Good evening, friends, colleagues, ladies and gentlemen. The IMS public lecture is an outreach activity of the NUS Institute for Mathematical Sciences. So this evening, the public lecture is also jointly organized with the Center for Quantum Technologies, or CQT, and we are honored to have Professor Charles Bennett as our speaker. Professor Bennett received his PhD from Harvard University in the early 70s, and since then he has been working at IBM Research Division for 40+ years. He has worked on various aspects of the relation between physics and information. So in '73, building on the work of Wolf Landauer, he showed that general-purpose computation can be performed by thermodynamically reversible apparatus that avoids throwing away information about pure past logical states. And in '82, he proposed the currently accepted way, the currently accepted solution of the resolution of the Maxwell-Steinman paradox, attributing the demon's inability to violate the second law of thermodynamics to the dynamical cost of destroying rather than acquiring information. And in collaboration with Jules Broussard, he developed a practical system of quantum cryptography, allowing secure communication between parties which share no secret information initially. And later, with the help of John Smolin, he built a working demonstration of it in '89. And so in 1993, Professor Bennett and his collaborators discovered the quantum teleportation, in which the complete information in a system is decomposed into a classical message and quantum entanglement, and then we assemble from this information these ingredients into a new location to produce an exact replica of the original quantum state that was destroyed in the sending process. So lately, Professor Bennett is interested in the emergence of classical correlations and computationally complex behavior from quantum laws, the theory being that thermal disequilibrium is necessary for this emergence, and that most classical information created on Earth is transient, eventually escaping into space as thermal radiation. So Professor Bennett has earned a lot of recognitions, awards, and honors for his accomplishments. He's an IBM fellow, a fellow of the American Physical Society, and a member of the U.S. Academy of Sciences. He is a recipient of the Wank Prize, the Harvey Prize, the Okawa Prize, and 4 honorary doctorates. Professor Bennett is currently visiting Singapore, participating in the IMS program Mathematical Horizons for Quantum Physics 2. And so this evening, the title of his talk is Quantum Physics, Public and Private Information, and the Lost Literature of Antiquity. So Professor Bennett, please.
Turn myself off. Can you hear me now? Can you hear me now? Yes. It takes a while for the capacitors to charge up. So actually that title was better than this one. Public and private information is a very important part of what I want to talk about. But there are, I think, some non-scientists or non-quantum information specialists in the audience. And I'm going to try to say something that seems a little implausible, that this arcane branch of physics has, over the last 20 years or so, taught us something fundamental about the nature of information that was there all along but was not appreciated until now, so that we have a better and more complete understanding of what information is than people through most of the 20th century. And this has to do with a lot of things, not just physics and not just even science. Like other parts of mathematics, the theory of information and information processing originated as an abstraction from everyday experience. And this is evidenced in even the words that are used. The calculation was originally moving pebbles around. And a digit, of course, is a figure or a toe. And we have had, over the last several decades, an information revolution, so that some ideas about what information is and what you can do with it that used to be only known to technical people, to engineers and scientists, are now everyday information. For example, the principle discovered by Turing that computers beyond a certain level of complexity are equivalent in what they can compute is known by everybody who goes into a computer store and says, is that program available in a version for my Macintosh? So people are very savvy, even every ordinary lay people are very savvy about the theory of information and computation compared to people in, say, 1900 or even 1950. Well, so this was a very successful abstraction. You can think of it as the difference between the fact that you can understand information and information transmission and computing in an abstract form of the software and the operations that are done, separate from the hardware. You can leave the hardware to the engineer, and next year you can buy one that's faster and it will do the same computation. It'll be better, and it'll be thinner. Like, that's very important to get it thinner, and it does the same thing. I remember my first personal computer that was called a portable, IBM portable. And it had, I think it had, it had 256 kilobytes. Can it be kilobytes? It wasn't megabytes. 256 kilobytes of memory. And it weighed about 30 pounds. And it was expensive. Anyway, so this was a very successful abstraction. But this abstraction of deciding what is the physics part and what is the information part and what is the mathematical part was done, I'm going to say, in a slightly too narrow way. And that the theory of communication and computation that was developed in the middle, or early to middle part of the 20th century left out some important features of information. And the most important thing that was left out was the quantum properties of information. Also left out properties having to do with thermodynamics and reversibility, which was mentioned in my biography. But the big thing they left out was the fact that what is information? Everybody really knows what information is. Information is the science of distinguishability, considered separately from the things that you're distinguishing. So that I can write something on a paper and then look at it later and remember what it was. And it doesn't matter that it was paper, it could be a stick of butter, or it could be a brick, or it could be an electrical circuit, and the fact that it has some number of distinguishable states, that's the information. Well, this information, the information carriers were viewed as what a physicist would call a classical system. That is, that their states in principle could be reliably distinguished and were not disturbed by observing. And then this almost would go without saying that if you want to specify the state of a system that has two parts or several parts, it's necessary to specify the state of each part, and also sufficient. So if I say this bottle doesn't have a cup on the top and this bottle does, then I've described the cupedness of both of those bottles. And if I said this one has a cup, I haven't described it because I didn't say what's the state of that one. Well, physicists had known for a long time, since like about the 1920s and 30s, that real things in nature, especially small ones like atoms, don't behave that way. That the science of the distinguishability of atoms doesn't behave that way. And that if you attempt to observe a small system, in general you will disturb its state. That actually doesn't sound too implausible. We know that's true in everyday experience. So that sounds like a scientist finding a complicated name for something that everybody already knows. But there was a particular form of this disturbance which was universal and unescapable. You couldn't measure something better by making a better measuring improvement. So there was some real content to that, and that was the most famous part of quantum physics, the uncertainty principle. And then a less well-known part was the fact that two particles can exist in a state that is not properly describable by is attributing a state to each one of them. So in other words, a violation of this thing that was self-evident, that in order to describe the state of two things, it's necessary and sufficient to describe the state of each one. So I'm going to talk about that because for some of you, at least, that's going to be a sort of unfamiliar idea. And if you take away anything from this talk, that should be what you should take away. To understand that idea. And that I then generally will use blue when I'm speaking of entanglement. So as I said, for most of the 20th century, the main way people thought about quantum effects, and the reason they didn't think about them in a very fundamental way, was that they were a nuisance, and they would cause some small electrical circuits to behave in a more random way than the ideal circuit would do. But now it's known that these quantum effects can have a positive use, and especially the entanglement is not only is it useful for various purposes, but it teaches us something about information, which is this thing I said before, which is that to describe the state of a system that has several parts, it is not sufficient to describe the state of each part. And that's like, in a way, a more fundamental revolution in the way we think than the idea that from relativity that there is not an absolute time separate from absolute space. Well, they're both pretty hard ideas to take on board, but I would say probably the number of people who have a basic understanding of relativity is greater than the number who can feel like they really understand entanglement. And I'm going to hope to say why this pervasive phenomenon of entanglement remained undiscovered until the 20th century. As I say, every time information exists in the world or is processed there was entanglement involved. And you say, well, where is this? How come it wasn't discovered until lately? Are you sure? Well, so despite the differences between the ordinary information that we're familiar with, which I call classical information, and quantum information, there's some parallels. As we know, as everyone knows, you can reduce information to bits, and it takes, for example, it takes about 8 bits to represent a character in a book, and the processing of the bits can be broken down into a sequence of ands and nots, basic operations. And that the form of the physical carrier doesn't matter, this is a slight abuse of the word fungible. In case you've never seen that word used to mean that, that's because generally it doesn't mean that. That exchangeable in terms of, it doesn't matter what physical system you put it in, as long as it has 2 distinguishable states. Well, there is a parallel now, and that is that quantum information, and this is an informational way of thinking about quantum physics that the chemists and physicists, it didn't occur to them to think this way, but that any quantum state can be reduced to describing some number of qubits. And these qubits are the quantum analog of bits, and that all operations or any change of a system, of a quantum system, can be described by operating on these qubits. And similarly, they're fungible. So what this says is that we ought to generalize our notion of information and information processing. And of course, information technology almost entirely lives in the classical part. And I'm not going to talk much about technology or about building a quantum computer. I may say a little bit about quantum cryptography, which it sticks out here into the quantum part. So let me try to give a intuitive feel for this other kind of information, because everybody knows what ordinary information is, the classical information. So what is quantum information like, without trying to use any mathematics? Well, I kept trying to figure out a way of describing it. I say, well, really, it's like the information in a dream. If you try to explain your dream to somebody, eventually you don't remember the dream anymore, you only remember what you said about it. And it's intrinsically private, like you can lie about your dream and you can't get caught. And you can't prove to somebody else what you dreamed about. A very private kind of information. But unlike the science of dreams, the science of this slippery, evanescent kind of information is well understood. It has very well understood mathematics. I'm going to review that so briefly. You will all have seen this stuff, some of you in Sunday school. So there are these laws, and it follows, it explains the relation between the mathematics and the physics. So we go on, there's some more laws. And it's a little bit religious. Oh my God, it's got this oh, well, I'm losing some funny fonts here. Okay, let's see what we might have to jump to the other version of the talk here. Okay, well, mostly I've got words here. So if you had to reduce the principles of quantum physics or quantum information down to one principle, it says that between, not all states are reliably distinguishable. Well, that's sort of, oh, so what? You know, I didn't think they were anyway. But the way states behave is they behave like directions in space. And the only states that are reliably distinguishable correspond to perpendicular directions. But it's not three-dimensional space. It can have a variable number of dimensions. Indeed, it has a number of dimensions equal to the maximum number of reliably distinguishable states. So if I'm thinking about this, it says I can have a state like that and a state like that that are reliably distinguishable. Or I could have a state like that and a state like that that are reliably distinguishable. But these two states are not reliably distinguishable, nor these two, nor these two. Has to be perpendicular. Or as a mathematician would say, orthogonal. And any direction is a possible state. So that this introduces some kind of mathematical order to this science of partial distinguishability. Now, let's give an illustration of that. One of the simplest quantum information carriers is a polarized photon. Now, I believe this laser emits polarized photons. You can't see polarization with your eye, but you can distinguish it. Let's see. Yes, it's polarized. Because the polarized sunglasses are based on the idea that a reflection from a surface, from a flat surface, one polarization is reflected more than the other. So if you take this beam of light and you reflect it off a shiny surface, and the amount that reflects depends on the angle that you hold it, and it shows that it's polarized. Most lasers are. So here, if I have a stream of photons, I can distinguish perpendicular polarization directions. For example, these horizontal photons are coming in like that. I can distinguish them with perfect reliability from vertical photons by sending them through a crystal of a calcite or any number of another type of materials. It's just an optical material that has sufficiently low symmetry in the shape of the crystal. And what happens is the horizontal ones go straight through, and I can count them in a detector here, and the vertical ones get deviated while they're in the crystal, and then they come out parallel to the direction they were before, but displaced, so I can count them in a different detector. And this means that I could use these single photons of light to carry 1 bit each. But suppose I put in some photons that are polarized at some angle, like that. Now the way you make those is, supposing this thing emits vertical photons, I can make a stream of diagonal photons by rotating it by an angle like that, or a stream of horizontal photons by rotating it like that. So you make it in a very easy way. And these diagonal photons, instead of getting deviated by an intermediate amount, which is what you might expect, they behave probabilistically. Some of them go into the horizontal beam and forget they were diagonal, and some of them go into the vertical beam and forget that they were diagonal, they become vertical. So this is that's just the fundamental quantum behavior that is pretty different from any kind of intuitive notion of partial distinguishability. It has very much this notion of perpendicular directions being distinguishable and non-perpendicular directions being not distinguishable, and if they have to do something to be non-distinguishable, they end up behaving probabilistically. So in other words, I could distinguish a large stream of vertical photons from a large stream of diagonal photons. But a single vertical photon I can't distinguish from a single diagonal photon, because there's nothing I can do to it that would reliably tell them apart. All that I could say was a vertical photon, if I send it into this crystal, will be deviated like that. And a diagonal photon, if I send it into the same crystal, it might be deviated like that, but what might be deviated, oh, you can't see when I point to it. Yeah, so it's, yes, a diagonal photon might be deviated or might be left alone, but if you had only one, you wouldn't know why it was left alone. Was it left alone because it was vertical, or because it was a diagonal one that was unlucky or lucky? So, and this also gives us the opportunity to choose what distinguishing we're going to do. So I can separate vertical and horizontal photons by a crystal in this orientation reliably, and that would randomize the diagonal ones. And I can separate the diagonal ones just by rotating the detector apparatus, but then that wouldn't distinguish these. So we have a problem that we can distinguish any 2 perpendicular directions, but we can't distinguish all 4 directions. And this is what is taken advantage of in quantum cryptography. Well, quantum cryptography was an idea that was based on an earlier idea, but less practical idea, of quantum money. Now, many, I don't think it's true in Singapore, but many countries used to print on their money a threat that is whoever falsifies or duplicates this money will be punished by some number of years in prison. Now the quantum money, it doesn't say that. If you read the Latin here, it says, I will not be duplicated. And the way it works is it has 20 perfectly reflective boxes, each containing a photon of one of those four kinds. And the bank knows what was written on the money. And if you are a counterfeiter and you want to take a piece of this money and make another copy of it, you must attempt to measure these photons. And if you look at them the wrong way, you will spoil them. And since there are 20 of them, the chances that you will fail to spoil any of them is not very good. So most of your efforts to falsify the money will not be accepted by the bank. And if there's any reasonable kind of penalty for passing bad money, you'll get caught. Well, it's not very practical because we don't know how to store a photon for more than a few milliseconds. So this money isn't good except in a country with very rapid inflation. But the photons are very good for transmitting information, and so the quantum cryptography uses the polarized photons to send the same sort of signal from one place to another. And then, and this was an apparatus that we built, I heard you mention in my biography, it was John Smolin and Gilles Brassard worked, and his students worked on the software to drive it. So we produced some dim flashes of light here, adjust the polarization here, and about 30 centimeters away, we rotate the polarization a little bit, or we don't rotate it according to this electrical device, which is called a Pockels cell. And then here's a calcite crystal that separates it into two beams where they're measured with two photon counters. So this has become much more practical in the subsequent years, including some proposals. I don't think it's actually up in space yet for putting these things in space and communicating over intercontinental distances. In fact, I think one of these experiments is supposed to happen this year in Singapore. So here, but getting back to the fundamental properties of it, I say that you cannot measure the polarization of a photon exactly. You can't determine, even though the photon might start off with a 28.3 degree polarization, there's nothing you can do that will find that out if you just have a single photon. If you have an unlimited supply of them, you can find it out because you rotate your apparatus until the maximum number of them get through into one beam, and then none of them go into the other beam, and then you know your apparatus is aligned with the photon. But if you just have one, you can't do that. Now, you also can't clone them. You can't take one of them and make a lot of copies that are the same, because of course if you could do that, then you could determine the polarization accurately. And this is a little surprising, and was a little surprising to the people who developed lasers. As I said, laser light is usually polarized along a preferred direction, but if you build a laser very carefully, you can build one that doesn't prefer one polarization over another. And ideally, if you send in a single photon, it would make a copy of it, of the same polarization. But lasers don't work well with a low input. A laser was originally an amplifier, and the way a laser works is it has some mirrors at the end, so the light goes bouncing back and forth a lot of times and gets amplified, and then you let some of the light out at one end. And if you try to use a laser as an amplifier, and you give it an input of a single photon, by fundamental laws of physics, it's just as likely to emit another random photon as it is to emit a copy of the one that you put in. So if you put in this, sometimes you get this out, but equally often you get that in a random one. And so that combination, it adds, in other words, just enough noise so that it doesn't help in the distinguishing problem. So this is an idea that's a little unfamiliar and hard to explain to people who are new to it. Indeed, even some of the founders of quantum physics I would say, impeded the public understanding of their subject by saying how hard it was. I've been people, I think Feynman said something like this: if this doesn't make your head hurt, you haven't been paying attention, things like that. Professor William Wooters, one of my collaborators at an undergraduate college, he's taught generations of undergraduates, and he thinks a lot about pedagogy. And so he says, well, here's what it's like. This way in which a quantum system, when you measure it, behaves in one of two ways, probabilistically. If you put it in a vertical way, it always goes here, horizontal always goes here, but if you put it in diagonally, it has to choose between those two. It can't do anything else. And he says, what that is like one of these strict old-fashioned schools where the teacher can ask the pupil a question, but the pupil is supposed to answer that question and not ask some other question. So, so the teacher is the measuring apparatus, and the photon is the pupil. And the pupil, for example, the teacher would say, are you vertical or horizontal? And the pupil starts to say, well, I'm polarized at about 55 degrees. I believe I asked you a question. Are you vertical or horizontal? Horizontal, sir. Have you ever had any other polarization? No, sir, I was always horizontal. So I said that there was a parallel between classical and quantum information in that even though this distinguishability business and the non-copying business behave very differently, you can break it all down into elementary units of just as classical processing of data. If you want to multiply two numbers, or you want to, if you want to sharpen up the picture of your grandchild because it was fuzzy, so you pass it through an optical filter, that can all be reduced to doing ands and knots on bits. So any processing you might want to do on quantum information, you can think of a bunch of qubits coming in on these wires, say photons, and then anything that you want to do to it can be involved operating on these photons one or two at a time, just as you can do anything with bits by working on them one and two at a time. Well, what are these operations that are going on inside the quantum computer? Well, the one bit operation, this thing that I've used a box with a U, it's called a unitary operation in mathematics. That's basically a rotation. I already told you about that. Taking a photon and rotating it by some angle is a 1 qubit operation. Now, what's an example of a 2 qubit operation? Well, we really only need one of them, and one of them is sufficient for that when you use it in combination with the 1 qubit operations, is the one that a mathematician or a computer scientist would call exclusive OR. The quantum information people invented a new word for it called controlled knot. But the idea is if we have so this is the controlling wire, we send in a vertical photon along here, and if this controlling photon is vertical, the one on this wire gets rotated 90 degrees. And if it's horizontal, the one on this wire doesn't get rotated at all. So that's the equivalent of conditionally flipping a bit. If the input that controls whether to flip it is a 1, it flips. If it's a 0, it doesn't flip. However, so that's an actually well-known basic digital logic gate. But this thing is not just a classical gate. It has to obey the superposition principle. So if I give it a diagonal photon, which is mathematically represented as the intermediate direction between horizontal and vertical, and I divide it by the square root of 2 to keep the length the same as it was before. What is this? So in other words, if I take these two directions and add them together, I get a longer direction there, and if I want to shrink it down to be the same length, I have to divide it by the square root of 2. So this diagonal photon is mathematically equivalent to the direction intermediate in space between, in this polarization space, between horizontal and vertical. And therefore, if I give it as an input, this processing, this gate, has to do the superposition of what it would have done if I gave it this input and what I gave it that input. So that's the state that's intermediate in not two-dimensional space, but four-dimensional space, between both of them being horizontal and both of them being vertical. So this is really an unavoidable consequence of the superposition principle. It says if you're given a superposition of inputs, you get the corresponding superposition of outputs. And even if the inputs and outputs are just directions in two-dimensional space, already you get this kind of state that has no classical way of viewing it, of saying it's a state of one photon combined with a state of the other photon. So what does this entangled state mean? It's the state mathematically that's equal to the intermediate direction between both photons being horizontal and both photons being vertical. Well, if you do the math on it, it turns out that it's also equal to the state that is intermediate between both of them being right diagonal and both of them being left diagonal. And it is not equal to any of these states like this, saying that they're each intermediate in direction between horizontal and vertical. So if you wanted to put it in words, you say that the photons are in a state of sameness of polarization, even though neither one has a polarization of its own. It's very hard to picture this because it's hard to think in four dimensions, and you need at least four dimensions to do this kind of superposition of things that have more than one part. But that's how it behaves. So let's try to do some metaphors for it. Well, I'm of the right age and nationality to have been in San Francisco in 1967 during the Summer of Love. And at that time, it was very easy to find people who thought they were in perfect tune with each other, even though they didn't have any opinions about anything. But they were sure they were in perfect agreement. And of course, they believed that if you have enough LSD, that everybody could be in perfect harmony with it. I guess it's illegal in this country, right? With everybody else. Now, they were not very good at mathematics, so they didn't understand the consequences of this You don't actually need anything more than the superposition principle to figure out that entanglement is monogamous, and that the more entangled two systems are with each other, the less entangled they can be with anything else. And that will have important consequences. Well, now I'll try to come up with a pedagogical analogy to entanglement based on Wooter's idea. So imagine that you have two pupils who are kind of a problem because they don't ever seem to learn anything. And if you ask them a question, they always give a random answer. But they always give the same random answer. So we have, I guess we've got Remus and Romulus, the twins. And one teacher asks them, what's the color of grass when it's growing? And he says, pink, sir. And another teacher asks the other one, what's color is the growing grass? And the other one says pink. You know. But another day they might say brown or something like that would be the right answer, or the green. So that's the way they behave. Now, what can you use this entanglement for? I'm going to tell you about teleportation. Now, it would seem that the uncertainty principle prevents taking a subquantum system like a photon whose polarization you don't know, and making an exact copy of it somewhere else in a photon, preparing another photon in exactly the same state as the first photon was, because you can't find out what the state of the first one is except by approximately finding out and maybe destroying it. So it would seem that this job, I'm thinking of time going up and space going left to right. So I've got a photon here, it's traveling along, and I want to somehow make another photon here in exactly the same state as that one was. And there is a way around this logic that suggests that you can't do it. And that is to do this. Well, before I say that there's a way around it, let's see what's the problem. If you try to measure this photon, you won't get all the information out, you'll spoil it. And so you'll get some information out, like you'll say it's more likely to have been vertical than horizontal. And then you do your best effort over at this end, and you get a copy which is not exact. It can be off in some way. It could be 45 degrees off in its polarization direction. Well, here's how you do it with entanglement. So you start off with 3 photons, the unknown one that you're trying to teleport, and then a pair of entangled photons that you prepare in one of these entangled states so that they're in, say, some state of sameness or a state of oppositeness. And then you bring one of these entangled photons together with the unknown one, and you measure their relation. You don't measure the polarization of either one. You measure the relation between the two. And since it's 2 photons and they each have a 2-dimensional space of states, you have 4 perpendicular possibilities in the 4-dimensional space. And you measure you make a measurement that speaks of the 4 different relations they can have without actually ever having a state of their own. And so there's 4 different ways they can do that that are perpendicular to each other. So I can't even show you. Anyway, that's a measurement which completely disrupts the states of those photons, but yields 2 bits of information, that is 4 distinct possibilities. And then what we do is we take this other partner of the entangled pair and we apply one of 4 different rotations to it. And when you do the math, it comes out in exactly the same state as this one was, except this one has been destroyed, so you haven't actually cloned it. You've gotten rid of it here, and you've taken apart the completed information into a part that can be transmitted classically, and another part that is transmitted in this very strange way. It looks like it's going backwards in time and coming forwards again, and it's just that part of this information that you couldn't transmit classically. So that's how you do that. Now, I also thought of a human analogy for that. So we have, nowadays everybody seems to be worried about terrorism. So, and if you have some complicated experience, maybe a scary experience, that's a little like a dream. And the more you think about it, you begin to remember what you said about it, not what you actually saw. So suppose that Alice has, in cryptography, we always have Alice and Bob. So Alice has witnessed a complicated crime, and she lives in Boston. And the Washington FBI know that her memory is in a very delicate state, and they want to ask her just the right questions. And some of these questions are even classified, so they can't tell it to the Boston police to ask her. And they want to ask the right questions in the right order. So they say, please come to Washington and help us with our investigation. Well, she doesn't like to travel, and she says no. And of course, they could subpoena her, but then she would become uncooperative, and that's worse than useless. So they have to send one of their agents to Boston. But that's not very good because these agents all have their own prejudices. And this one was, no, you're not going to ask her that question first. No, you can't go. So finally they decide they can't do it. Except that that's one of these FBI guys who happens to be Remus volunteers. And he says, I don't know anything about this case, and therefore I won't influence her at all. And I like to travel. I just asked my brother. And Romeo says, yeah, he likes to travel. We both like to travel. So they send Remus to Boston, and they have a speed date. And the idea is they're not supposed to discuss anything substantive. They just figure out whether they like each other or not. Well, it turns out they don't. So the Boston police call the Washington FBI and say that Remus doesn't get along with Alice. And they say, good. Okay, they go now to Romulus. Well, it seems that Alice doesn't get along with your brother, so we'll ask you all the questions we would have asked Alice, except we have to reverse all the answers. And so that's I don't know if that makes any more sense. But maybe just the idea is getting familiar for having heard about it so long. So the reason that people are interested in, the biggest reason that people are interested in quantum information isn't quantum cryptography, which is somewhat useful, or these quantum teleportation and these paradoxes and things like that of entanglement. It's because of quantum computers, which don't exist yet. And the idea that if they did exist, it could help speed up some hard problems of computation. And here's an example of one that would be much faster to solve on a quantum computer. this is the problem of taking a number which is the product of a whole number, which is the product of two other numbers, and finding out what two other numbers it's the product of. Now, the problem in this direction, going from these numbers, the factors, to that one is relatively easy. You could do it without a computer if you had a quiet weekend. 3 times 7 is 21. That's where that one comes from. You carry the 2. And then we've got another 3 times 7. So, you know, if you had a big pad of paper and we're not being disturbed too much, you could do that one. But this one, going in this direction, is way harder if you break it down into ordinary ands and nots, as I've shown here. It's a very hard computation. And you could probably do it faster now because computers are getting ever faster. But a few years ago, it took 8 months to do this on hundreds of computers working on it at once. For classical computers, factoring is exponentially harder than multiplying, but for quantum computers, both of these jobs would be about equally easy. Now, so I've been saying that information really is quantum, and you want to learn to think about information as being quantum rather than classical, and that classical information is just a special kind of quantum information. And I guess if there's some mathematicians here, it's like saying, well, we all thought we understood numbers as real numbers, but there's another kind of number, more general kind of number, complex numbers, that includes the real numbers as a subset of them. So I'm saying we have now the duty of saying, now we have to think in quantum terms. What is the meaning of classical, what's the meaning of a bit, if we're going to define it in terms of a qubit? And so the answer to that is that we choose 2 arbitrary perpendicular directions, and we call them 0 and 1. And a classical bit is a qubit that has one of those values. Boolean values named after George Boole. And a classical wire is a wire that conducts those 2 values faithfully, but is not guaranteed to perform well on superpositions of them. And the reason this typically happens is that the data passing through a classical wire interacts with its environment. The wire, in a sense, has an eavesdropper that's trying to see what information goes through. And that can be represented by this simple circuit. We have a wire, and as remember, the meaning of this controlled NOT gate, or this exclusive OR, is that whatever value goes through here, if it's a 1, this thing gets rotated. If it's a 0, it doesn't get rotated. In other words, if I put in 0, 0, it comes out 0, 0. If I put in 1, 0, it comes out 1, 1. If I put in, well, there's 2 other possibilities. But if I put in here something that is not a 0 or 1, instead of getting a copy of it down here, I get an entangled state, like I showed you before. And in this case, when the environment is eavesdropping on a wire, the extra copy gets lost. It gets thrown away into a place where it's hard to retrieve it from. So what this says is that the mapping between classical and quantum is that a classical bit is a quantum bit in one of 2 standard orthogonal states. A classical channel is a quantum channel that conducts those faithfully, and the reason it happens is it has an eavesdropper, and those are the only 2 states that the eavesdropper doesn't disturb by eavesdropping on. And a classical computer is just a quantum computer that has eavesdroppers on all its wires. So people ask sometimes, how can a quantum computer do these amazingly hard problems? And then they say, oh, it does it because it's in exponentially many different states at the same time. And then somebody else will say, well, then why can't it solve really hard problems like the traveling salesman problem, where you just have to explore 2 to the n possibilities, and if one of them says yes, then everybody says yes. Oh, we say, well, a quantum computer doesn't seem to be quite that powerful. Well, the reason, and anybody who works in quantum computing, and especially if you're talking to funding agencies, they say, we have only 2 quantum algorithms, and you've been working on this for many years. We want another quantum algorithm. Why can't, show us something else that quantum computers can speed up? And the researchers say, well, we've been trying very hard, but we only find these 2 things that it speeds up. I think that kind of anxiety can be relieved by realizing that a quantum computer doesn't speed up classical computations. Computations are intrinsically quantum, and that if you are handicapped by having eavesdroppers on all your wires, a few kinds of computations get slowed down seriously. So it's as if there are some kind of calculations that you can do. Let's say, imagine that you're a stay-at-home mom, and you have several kids, and you're trying to do a calculation, and or a stay-at-home dad. And I had some experience being a stay-at-home grandfather. And so there's certain kinds of tasks that I can do even if the kids are talking to me at once and asking me all kinds of questions. And certain other ones I make no progress on. So apparently there's some kind of computations like factoring, which are really sensitive to having somebody looking over your shoulder. And then some other ones like addition and multiplication, it doesn't matter. Okay, so now I want to say something about where this quantum randomness comes from and how that affects our ideas of determinacy, of, well, like how well can we predict the future, how well can we remember the past. Now, the classical picture of this that came from classical mechanics of the universe as like the solar system, as a piece of perfect deterministic clockwork. There were many ideas, many people of that era. This would be I think it would be like the 18th century was well established. But I think the most famous expression of it was by Laplace, who thought that the future and the past, as they are in Newtonian mechanics, completely determined by the present. So if you knew exactly the present state of the universe, you could figure out its entire past and its entire future. And there would be no mystery about it. And so that therefore to figure out which button to press. So therefore our lack of predictability of the future has to do with limited computing power. But in the quantum way of looking at it, if you think of it just in terms of the uncertainty principle, it would say that, well, the future is less determined. Even an omniscient God would not be able to predict whether a particular radioactive atom will decay. This was a very surprising thing about radioactivity. If you said you go to a hospital and it's full of people that are sick, and by tomorrow some of them will be dead, well, you could examine the people and find out something about them that would give you a lot of ability to predict which ones would survive. But there's nothing that you can do to a bunch of radium atoms that will help you pick out the sickest ones from the other ones. And there were a lot of attempts to do that. Now in our familiar world, we've got a lot of asymmetry between the future and the past. And we remember the past well, better than we can predict the future. And now there's a kind of a quantitative way of expressing that truism, and that is, they call it the Google Ngram app. And so what it does is you put in a phrase or a word, and it searches through all the books that were published as a function of which year they were published, and it tells you how often that phrase appears. So here's an example. If you take the phrase 1970, it's mentioned a little bit in the 1960 and 1965. Just before 1970, it gets mentioned a lot, and then it gets mentioned even more about 1972 or 73, and then it just starts dying off much more slowly. And similarly, in the other years, the same thing happens, but it's just shifted by 1 year. Now, there's always exceptions. If you used 1984, it would be mentioned before because it used to be the title of a book. And if you mentioned 2000, it would be mentioned a lot because people were worried about their computers breaking down. But most years work like that. So, but unlike the future, remember the Laplacian worldview was we can't predict the future because we're not good enough at computing. But we ought to be able to remember the past. So it was considered that past microscopic events, even like whether a radioactive atom decayed or not, well, it either did or didn't. And so that should be definite and unambiguous. Am I getting too loud? Should I move this down a little farther? A little too loud? I'm okay, okay. So some microscopic events in the past, like which path a particle followed when you're not looking at it, if you have some quantum sophistication, you would say, well, now that wasn't really something that happened. It's not, you can't say, we didn't look at it and it was either here or there, but it was one of those places. Because that idea, thinking that it must have been somewhere even when you weren't looking at it, leads to the contradiction by way of this experiment, which involves an interferometer. This is equivalent to the famous two-slit experiment. So an interferometer, how many people here have not heard of an interferometer? Okay. So an interferometer is an arrangement of mirrors and half silver mirrors where the light has half a chance of going through, or half the light goes through. And you line it up very, very carefully so that this distance is exactly equal to that distance, and this distance is exactly equal to that distance. And then what you find out is that if you shine a beam of light in here, half of it goes here and half of it goes there. And then, of course, it bounces off the mirror, and the same half that went here comes here, and here like that. And then when it hits this mirror, instead of half of it coming out here and half of it coming out there, it all comes out here. So that's, you can explain that by the interference of the waves, if you think of light as a wave. But if you think of it as particles, that's a little strange. How can the particles know? Well, so, and this is why it's really strange. Let's say we interfere with this experiment, we obstruct it by putting our finger in the way of one of the beams. So naturally, half of the photons are lost because we stop them, and the other half will come down here and they hit this other beam splitter, and half of them go here and half of them go here. So by blocking off some of the light, you make more light come out here than came out before, because it used to be none coming out here. So the idea that a photon comes along and hits the beam splitter, it's a little bit like a polarized photon hitting a calcite crystal at the wrong angle. It might go here or it might go here. That's not really the complete story. It goes in a superposition of doing those two things. And so let's try to understand this a little bit more deeply. So if I leave both paths open, the photon leaves by the same exit as the corresponding exit to where it went in. And that indicates that while it was not being observed inside the apparatus, it was following a superposition of the two paths. It wasn't maybe being one path or maybe being the other path. And so after the experiment, even God doesn't remember which path the photon followed. Now, people have different ideas about God, but I asked one of the grand old men, he's even older than I am, of quantum information theory, Danny Greenberger at City College in New York, about this and what he thought, does God know? And he said, any God who would want to know that, I wouldn't believe in that God. So this superposition looks like a very different thing from this brutal irreversibility of measurement that I just described, with the pupil saying that I'm forgetting that he was ever at diagonal. So how do we harmonize those views? Well, they're harmonized by the notion of the monogamy of entanglement that I talked about before. And you don't have to read this slide because it sort of says what it said before. Oh, it says a little different. Most systems in nature, other than little ones like photons, interact with their environment so strongly that they become massively entangled with it. And this destroys the entanglement between the parts of the system by the monogamy. So that's why you don't see entanglement. Why entanglement was, the world was full of entanglement, but nobody discovered it until the 20th century. It's like the parable of the fish. The fish is asking the wise old fish where the ocean is. So this is expressing the monogamy of entanglement. If A and B are perfectly entangled with each other, they cannot be entangled with anybody else. They can't even be classically correlated with anybody else. They have to look completely random to anybody else. And suppose B tries to share his entanglement with a third party, or let's it gets eavesdropped on, then that degrades his entanglement with A into a mere classical correlation. So supposing we have some unknown quantum state, we let it interact with an environment, and this produces the entangled state, in which each part looks random, but we could undo this entanglement by letting it interact again. But then before that happens, we let one of them interact with another environment and throw it away, and then we're stuck with the thing where these two are not perfectly in harmony with each other. They are only somewhat correlated. So let's look at the origin of quantum randomness from this entanglement point of view. So we have these photons coming in here and splitting into these two beams. Of course, I've drawn the photons as if they were in the beams, but nobody has looked at them yet. This is a kind of a cartoon or a approximation. So let's take those two beams and not measure them. We don't have any detectors, so take away the detectors. And then I'm going to put the word behavior in quotes. The idea that it might go in here, it might go in there, is actually a bad idea. And therefore I can say that their behavior is undone. It's possible to undo it. What we have to do here is before we put the second crystal, we have to put, or before we put any detectors, we put in a piece of material that has the property that it rotates horizontal photons to vertical ones and vertical ones to horizontal ones. You can use either a halfway plate or a piece of sugar solution that rotates photons. In other words, you do a unitary or 1 qubit gate on this thing. And then what happens is this crystal will then put them back together, and instead of maybe coming out in one beam or the other, they come out, they exactly recover their original polarization. So let's look at this in terms of the metaphor of the student and the strict teacher. So what happens here is that it hasn't really done one thing or the other. It's still doing the superposition of them. But what makes the student forget his previous polarization is the public embarrassment of being asked about it in front of the whole class. That's a sort of a excessively humanized way of saying that, but this can be developed into a theory of origin of classical behavior from quantum interactions, and helps us to say what it means for information to be classical. And this is a theory that has been developed lately. I mean, there are many approaches to it, but the approach that I find most congenial is the one that is developed by Wojciech Zurek and his students. And he calls it quantum Darwinism, which I think is a bad name for it, and I keep trying to get him to change it, and call it quantum spam. And the idea is that if you have a quantum system that interacts with some eavesdropper, but not just one eavesdropper, a lot of eavesdroppers that eavesdrop on it in the same way, then what happens is that part of the information in this system gets redundantly copied into all these eavesdroppers, but the rest of it gets hidden. So if we break the system into the system itself and the environment, they remain perfectly entangled, but the system is only classically correlated with the individual parts of the environment. So if we lose any of this environment, it looks like one thing happened to the system and all the classical observers will agree as to what it was. And yet, if you got all those observers together and undid their observation process, the system would be put back into exactly the state that it started at. So this says information becomes more classical by becoming less private. Now, speaking of privacy, there's not too much of it around anymore because we have these cheap video cameras all over the place, and governments and other institutions that say, well, why not save all this data? I mean, what's the harm in saving it? We might need it someday. And I guess lately the consensus is that it's maybe gone a little too far in that direction. But these recordings are not always bad. They have some positive aspects, such as deterring misconduct, both individual and governmental misconduct. So maybe it's not a totally bad idea, and in any case, it's sort of unavoidable nowadays. So here's what we should say. Of course, when I give this talk once before, when Mary Beth was here, and I asked how many people in the audience actually have a gun with them. Well, she doesn't. You own one, but you don't have it with you, right? So anyway, in the United States, and there's some arguments that can be made for this, is that it protects people from despotism if people have the right to be armed, and of course other people, probably including myself, definitely including myself, thinks that the number of people who accidentally get killed by that exceeds the benefit. So I don't think it's a good idea.
It's not always accidental.
Oh yeah, right. Well, on the other hand, if you're a real libertarian and you say you want to kill yourself, you shouldn't be made difficult to do that. Or maybe, but if you want to kill somebody else, then it's more probably you should get their consent. Anyway, but I think a much better idea, instead of everybody carrying a gun, would be everybody having a camera. And then the idea that it should have some laws about this. You should be able to use your camera to document injustice and crime, but not for blackmail. And this is not a terribly new idea. A few years ago, maybe nearly 10 years ago, I saw a billboard in Delhi saying, every citizen a photojournalist. If you see it, shoot it. And this was before smartphones became as prevalent as they. Now, this is a good question here. How many people in this room are carrying with them a camera? So, in the contest between guns and cameras, there's way more cameras now. Now I have one camera here, but I'm feeling quite naked because usually I carry another one with, say, for better quality pictures. And then I have a third one in my backpack. So,
we're in US.
So anyway, what does this have to say about? Well, that's just I don't know where that leads socially, but well, I guess I could say that I never. The CNN has, of course, has activities in the United States, but they don't use exactly that ad in the United States. So it seems like there's three levels of privacy. There's the quantum level, like the path of an unobserved photon, which you can think of maybe never having existed. And then there's secrets, which we would normally call secrets, which a few people know, and they're not widely known, but they're classical. And then there's public information of the sort that politicians lie about. And this looks like the world with all these cameras and the easy recording looks to be very different from the ancient world, where in many cultures, or practically all literate cultures, there were famous works of literature that don't survive. There are no copies of them left that we know of. So just the fact that something became public at one time doesn't guarantee that it stays public. And yet we're warned that the internet is an irreversible medium of publication. If you say something embarrassing about yourself, don't expect it to ever be forgotten. So here's one of the examples of that, the Greek poet Sappho. And nobody knows exactly what she looked like, except she had dark hair, because some of her poems said that. And this happens in different ways in all sorts of societies. And I'm not an expert on Chinese history, but the Emperor Qin Shi Huang, who was, I think, in unified China, he thought it was important for good governance that conflicting ideas to his own should be suppressed. And so he ordered that a great many books about history and things that were of any sort of controversial nature would be burned, and I think that anybody who was found harboring them would be executed. And some of the Confucian scholars wanted to protect the books, so they just memorized them, and they rightly predicted that this government policy, and even I think this emperor didn't last too long, so within their lifetimes they were able to write them down again. But some of them were lost. Now Sappho's poems suffered a more mundane loss, just because the dialect of Greek that she wrote in was no longer spoken. It was hard to understand. So although scholars and literary people thought she was a great poet, most people didn't read it. There wasn't demand for it. And the paper, or I guess it was it papyrus, or what they wrote on in those days, was valuable. It was reused for other purposes, like wrapping up mummies. So occasionally when they unwrap a mummy, they find a fragment of poems from Sappho. So there was just like about 10 years ago they found it. The number of complete poems that they had of her went from 3 to 4 because of a piece that they found that way. Now, this I've asked some of my Indian friends about this, what they know about this, but apparently there was a school of philosophy which might have been the first atheists, and it survived for a long time, and all that we know about it is what was said about it by its opponents. So we have those things on a large cultural scale. But then in a much smaller scale, there's information that becomes classical, and yet it gets lost because nobody bothers to record it. And of course, how do you prove that such information exists? Well, you record it. So here's an example of it. Back in 1965, I took a picture of some riverbed which had had a rainstorm, and the drops landed on it while the mud was soft and wet. And then it all dried out and the mud's cracked. And I thought it was an interesting pattern. And then, of course, this being Las Vegas, a desert climate, and a few days later there was a big rainstorm. It got all washed away. So the question is, what's the fate of this classical information? Or what would be the fate of it if I hadn't taken the picture? So it's tempting to believe that any such macroscopic information, to believe in the sort of the Laplacian picture that the world is reversible, and that in principle, if I burn a book, I don't destroy the information in it. I just scramble it, and it gets converted into the smoke and the ashes, and very importantly also the photons, the heat that are produced by burning the book, the heat and light, because that's a form of information, and that goes out. And if I were able to collect all this stuff and undo the process of burning it, I would get the book back. And so therefore, maybe every classical phenomenon is like we fear about the blogosphere, it's there for good. And so persons like disappeared under suspicious circumstances, like Jimmy Hoffa or Jim Gray. I think this is not actually a sign that that's a dangerous first name to have. Could be recovered, and they have their fate is unknown, but it's not non-existent. And I had a strong prejudice in this direction myself because I was annoyed by the postmodernists who critics of. Is that me? Oh. Postmodernists who said that the idea that there is history, that there is a past, is a wrong idea. That the history is what we think happened, not what did happen, and that objective reality doesn't exist independently. Well, that's just an idea that to most physicists and maybe other natural scientists seems like egregiously anthropocentric, that the universe should depend on us is, well, you can say things on both sides of that, but it generally doesn't feel congenial to physicists. So I didn't like that idea very much. But then I did some calculations, and I became convinced that most classical information is not retained, at least not retained in the place that we can get it. And that's because there's a vast flow of random information into the Earth and out of it in the form of photons. And the Earth is big, but it doesn't have an infinite storage capacity. And the amount of information that's flowing through it is so great that it has no ability to save it all. So if you calculate the rate at which information is leaving the Earth, it turns out to be around 10 to the 30th bits per square meter per year. And a somewhat smaller amount is coming in from the sun. And you say, well, if the Earth was going to try to store all this stuff, where would it put it? Well, the main thing that's being newly made near the surface of the Earth is rock in the bottom of the seafloor where the plates are spreading apart. And so new rock is solidifying. And it's got a thickness of, what, 10 kilometers or so. And we could say, well, if you were trying to use rock as a tape recorder, how much information could you store? Well, probably around 1 bit per cubic nanometer. That's, are you going to put a potassium atom here or are you going to put a sodium atom there? And it's locked into this rock and will stay there for millions of years. And the rock lasts for about 100 million years before it gets melted again. So ends up that it's only able to store 10 to the 22nd bits per square meter per year. So it looks like it's got a serious shortfall. So this says that a lot of this information has to leave the Earth, and once it does that, you have a hard time catching up with it because it's going at the rate of the speed of light. So we have this new level of privacy of information, the quantum, the escaped, and then the classically private, and then the public and permanent. So here, let's try to classify some of these mysteries of the past. Now, one thing that's pretty secret, but is pretty clearly still on the Earth, is that in the city of Venice, they had a custom for, I think, over 100 years of going out into the lagoon with a gold ring, like a wedding ring, and throwing it into the water and letting it sink down into the mud to symbolize Venice's marriage to the sea. And so these rings are probably all still there, unless somebody got really lucky with their lobster trap. And then we have these lost classical writings that could be there or not, just depending on the luck of what happened to that particular piece of papyrus. Was it burned, or did it get used to wrap up a mummy? And then there are things that we're pretty sure are escaped because we know that nothing happened to fix them in permanent form. Like, I always use the example of where the raindrops fell in this morning's storm, or maybe a storm from last week. So suppose you were one of the gangsters who murdered Jimmy Hoffa, and you wanted to make sure that the evidence of your crime was physically inaccessible. So how would you do it? Well, of course, you would want to cremate his body and let the smoke and the heat escape, and then dissolve the ashes into a clear liquid so that you didn't have any fragments. And then, of course, you shouldn't tell anybody about it. And probably, because there might be some record physically in your brain that would survive in the connections of the neurons or something after you were dead, you ought to have yourself cremated. Well, anyway, this is ranging pretty far afield. So, well, can we arrange for this escaped information to come back? Well, yes, it could be that there's a mirror out in space or somebody's listening to it and is going to broadcast some of it back to us. But, and you might say that some of this information is a kind of an extraterrestrial fossil. But you couldn't get all of it back. Suppose, if you wanted to get all of it back, you'd have to get all of this thermal radiation that goes out and have it come back. And if you did that, you would eventually it would get pretty hot in here. Or actually, it wouldn't get hot because you would have shut out the sun by the same era, but the Earth would come to thermal equilibrium, which I'm going to talk about a little bit later. So let's look at this randomizing dynamics. So we have these raindrops. They fell, and they fell one place rather than another. But let's imagine that this hard record of it gets obliterated by, say, a subsequent rainstorm or evaporation of the drop. So let's look at it in quantum terms, as I showed you how to do with this picture of entanglement is explaining randomness. So this is the ontological status of escaped information. So the drops, suppose we have a raindrop that can fall in one of two places, left or right. And eventually it falls and forms and evaporates, and then all the earthly record of where it fell is gone out into the sky. So the picture of the quantum state, again with the square root of 2, I use this earth-colored letters to represent the terrestrial degrees of freedom, and the blue sky-colored ones representing the celestial degrees of freedom, the photons traveling away in space. So it's as God sees it, it falls in a superposition of places. But the terrestrial degrees of freedom all agree, and and so we don't see the superposition, we just see one side of it. It looks like classical information. It's random to us. But the global state of the universe is actually in a pure state. And the question of where, like if you asked God where it fell, he would say, well, I don't know. It fell both places. And if it looks like it fell in one place to you, that's just the accident of your viewpoint. Well, then eventually the terrestrial degrees of freedom are obliterated, and the more celestial ones, and eventually it's all in the sky. So we say the Earth is in the same state as it was before the rainstorm, and the sky is in the superposition of two states. And then it becomes somewhat questionable as to whether it means anything to say, where did the raindrop really fall? If there's no information about it left, and if you can think quantumly of the entire remainder of the universe as being in the superposition of places where it might have fallen. So the distinction between what happened, what did happen, and what might have happened but didn't, I'm arguing that that is a temporary distinction in the case of many kinds of information. And the stuff that escapes is almost the same as the two paths of a photon and interferometer, where both things are equally real. And this was an idea that was dear to John Wheeler, and he said the past exists only insofar as it's recorded in the present. So this is actually sounds like a very postmodern idea, except that it's not anthropocentric anymore. So this is actually part of popular culture. You can get a plaque to attach to a tree or something like that. It's in 1832, nothing happened here. Well, let's see, how am I doing? I'm just about taking up, what, an hour and a half, right? Yeah, I could go on, but I think I've gone on long. Come to a good stopping place. Well, I don't know. I certainly have more to say. This is a question. I don't know whether this evening lecture, can you handle another half hour? I think we better, maybe we should. Why don't we have like a refreshment break, and if anyone wants to hear the last part of it, they can come in afterwards. Do we have refreshments? No. Oh, there's no refreshments. All right. Oh, you got water. All right, we got water. All right, let's call it a day. And anybody wants to see me after class, we can talk about some stuff. Okay.
Any questions? Any questions? Okay, if not, let's thank Professor Bennett again. Okay.
I was going to say, if there's no questions, I don't want to
also, I would like to present a small gift to Professor Bennett for his wonderful lecture. Okay.